Welcome everybody to our next video in our series on probability and statistics. I, as always, am Dr. Lathram, and today we'll be continuing with our discussion of the family of binomial distributions. So from where we left off, we were discussing the family of binomial distributions. We had defined them, and we had talked a little bit about how we verify that they are a probability distribution and a family of probability distributions. And so now let's continue with kind of one of our workhorses that will help us figure out information about them, and that would be the moment generating functions. So remember that we've already talked about moment generating functions and how they're defined in a previous video. So if you want to go back and take a look at that, I encourage you to do so. So let's figure out what the moment generating function is going to be for our family of binomial distributions. So let's suppose that we've got a random variable y, and it has a binomial distribution with n and p as going to be the parameters. N is going to be the number of trials that we're using, and p is going to be the probability of success on a single trial. And so the definition of the moment generating function, so m sub y of t, is just going to be the expected value of e to the ty. Well, we've defined the probability density function for binomial distributions, and so we just multiply that PDF by e to the ty, summing over all values from 0 up to n. Then we do a little bit of algebra, and we can put the e to the t together with the p, because both of them are to the y power using our properties of exponents. And then, quite naturally, what we have is, by the binomial theorem, that is the binomial theorem applied to p e to the t plus q raised to the n power. So our binomial theorem really just kind of gives us what the moment generating function is automatically. That's kind of a nice, powerful way of getting things. And so now if we wanted to know, well, what is our mean for a binomial distribution? Well, for that, we can take the derivative with respect to t of our moment generating function, evaluate that at 0. So kind of remembering some of our calculus, we take the derivative of the moment generating function, we get n times p e to the t plus q raised to the n minus 1 times, so that's the derivative of the outside, and keep the inside the same, and now times the derivative of the inside is just p e to the t. So kind of making you recall a little bit of your chain rule there. And so if we evaluate the derivative at 0, we end up with just the expected value of y just being n times p. Now if we want the variance, now we have to take the second derivative. So taking the derivative of the first derivative, we get kind of this long and drawn out expression. So I'll leave that for you to try that on your own. Make sure that you come up with the same value. And then if we evaluate that at t equal to 0, we get our second moment being n times n minus 1 times p squared plus n times p. Well, then if we want the variance, then we take the expected value of y squared minus the expected value of y squared. And so what happens in that case, that's really going to be our second derivative evaluated at t equals 0 minus our first derivative evaluated at t equal to 0 squared. So if we plug that in, do a little bit of algebra, and we find that our variance just ends up equaling n times p times q, or n times p times 1 minus p. So now let's look at kind of the quintessential example of where the binomial distribution would be applied. So the question is, suppose that we have a student, and that student is taking a multiple choice exam, and that exam has 15 questions. For each question, there are 5 possible answers, and only one of those answers is a correct answer. So the first question is, if the student answers by guessing, what is the probability that he or she will get 10 answers correct? And kind of to follow that up, how many questions would we actually expect a student to get correct if he or she is only guessing at the answer? So that's kind of a pretty good question there. And so the setup for that problem, we have y being a random variable, just being the number of questions that a student gets correct from guessing. So that's going to kind of be the thing here. We're doing this as part of a kind of a random process, and so we're looking for just true or false. So by guessing, so if y is going to be have a binomial distribution with 15 possible questions, and the probability of getting a question correct is just 1 out of 5. And so the probability that y is equal to 10, so that the student gets 10 questions correct, is just going to be 15 choose 10 times 1/5 to the 10th power times 4/5 to the 5th power. Now, 15 choose 10 is going to be 3003. And so it's really those extra exponents. That really just gives us a probability of 0.000100764. So that's really not likely that the student is going to get 10 answers correct just by guessing. But then for the second question, well, how many would we actually expect the student to get correct if they were guessing? Well, for that is exactly what we mean by the expected value. So on average, if we perform this experiment over and over and over, so we've got a whole bunch of students, what would we expect the average value to be? Well, from our previous calculation, that was just n times p, so 15 times 1/5. So we would only on average guess that the student was going to get 3 problems correct. Now let's take a look and see what R can do with our calculations with our binomial family. So let's get R started. So type it up, here we go. Now, when it comes to our binomial family, there are several functions kind of associated with that. So let's just take a look at the help file and see what we have. So for the binomial distribution, what we see, we've got density distribution function, quantile function, random generation, and these are all listed here under the usage. So the d binom, that's for the probability density function. The p binom, so what the p binom is talking about, that's our cumulative distribution function. The q binom is the quantile function, so it's kind of the inverse function. So, and then the r binom is for the random sampling using binomial distributions. So if we take a look at kind of what our parameters are for the size, so for the number of trials that we want, that's our n parameter for our binomial family. And then prob is the probability of success on a single trial, so that's our parameter p. Now a couple of other things, this lower tail and being true or false. So when we're talking about the cumulative distribution function, we can either talk about the lower tail, which is going to be the probability that x is less than or equal to x, but if we would put the lower tail being false, then we're looking for the complement of that, so the probability that x is strictly bigger than little x. So that can come in handy and kind of save us some time with our calculation values. So now let's go ahead and get started with our actual problem. So for what we were doing, let's see, we had in our problem, we had 15 questions on our exam, and we had 1 out of 5. So we'll use the probability density function, So we want to know what's the probability if we have 10 questions correct. We have 15 possible questions, and the probability of getting a correct answer is just going to be 1 out of 5. And so if we put that in, sure enough, we see this is exactly the value that we got before when we had to calculate it by hand. So we can have R actually calculate our binomial distributions, or probabilities for our binomial distributions for us. So that's good. That can save us quite a bit of work on things. Now, if we wanted to calculate, say, what the probability density function would be for all the possible values, we can put in a range, so 0 to 15, so that's our entire sample space, so 0 to 15 correct, again, n size of 15, probability of success 1/5, and so R is going to return us a vector, so of the probabilities for each particular value. We can have that listed. We can save that as a vector, so let's save it as a vector, and then so we'll call that the PDF, so the probability density function. Then for our output value, so our sample space will just be, we'll call it Y just to be consistent. So Y being the range between 0 and 15, including 15. So if we check that, yep, we got all our values between 0 and 15. We can plot the values of the density function, and so we see that we get a graph that looks something like this. So it's discrete, so we just have these probabilities in here, but we can see this kind of peaked distribution, kind of small on the ends, gets really high, get a maximum value, and then kind of tapers off. So that's typical of what we would see for a binomial distribution. Well, now that we have those values, we can have R actually calculate what our expected value is by hand. So remember, we do that just by summing Y times the PDF values. And so sure enough, confirms our values for the mean of 3. If we do the second moment minus the first moment squared, so that gives us a calculation of the variance, we get 2.4. So that's our sigma squared, so that's n times p times q, so we get 2.4. And then for the standard deviation, so for our standard deviation, let's see if we can take the square root. So sigma being the square root of all of this. And so our standard deviation becomes, we can see square root of that's going to be about 1.549. So that kind of gives us an idea of spread of our distributions. So now let's look at a little bit of random sampling from the binomial distribution. So we know that between one standard deviation above and below the mean, we're usually going to get about 68% of our data. So let's calculate what mu is. So we'll save that as a value. So we know that was 3. Yep. And so mu plus sigma and mu minus sigma is going to be about 1.45 questions and about 4.5 questions. So it's probably somewhere between 2 questions and 4 questions. We would expect about 68% of our students to get between 2 and 4 questions correct if they were guessing. Between 2 standard deviations, which would take us up to about 6 questions. Then, all right, let's do some random sampling. So let's say that we take a random sample of 500 students, again with our parameters, n being 15 and probability of success being 1/5. And so we get, see what the results are for our students. So now we've got a bunch of students guessing on this exam. Let's take a look at what the data looks like, and there are possible values. So let's say that we had 500 students taking this exam. They were all guessing. Nobody studied that night. They're all guessing because this is just a random process. So if we look at the number of students that score between 1 and 2 standard deviations, we see that, or between 1 standard deviation above and below, we have 352, so 352 out of the 500. We would expect about 68% in our case, in this particular sample. Not too bad. We get about 70% of our data. So general rule of thumb calculation seems to be consistent in that case. So if we look at the values between 1 standard deviation, or between 2 standard deviations above and below, well, again, pretty close to what we would expect. I mean, in our sample, we get about 98% of the students between 2 standard deviations of the mean of our distribution. And so I think let's see, do a little bit more. If we look at the cumulative distribution function, we haven't talked about the cumulative distribution function yet. So the cumulative distribution, how many would we expect a student to, so what's the probability the student's going to get 10 or less problems correct? Well, 99.9999875. So between 9 questions correct. So this is our cumulative distribution function. If we look at what the lower tail does, then the lower tail is just going to give us the complement of that value. So the complement of the probability of getting 9 or less questions correct. So the lower tail equal false gives us the probability of getting 10 or more questions correct. And so if we just check that by doing 1 minus, so let's go back up here, 1 minus that value, and sure enough we get the exact same answer. So what the lower tail equal to false does, just switches the values, give you the complement for what the cumulative distribution is going to give you. And so this, I hope, has given you a little bit of an insight into the kind of capabilities that R has for making these calculations with the binomial family. And hope you enjoyed this. Hope it gives you a little bit of insight, and look forward to seeing you all later. Talk to you later.